Good evening everyone. I welcome you all for the 11th week tutorial for the course of Modern Digital Communication Techniques. So like every week, this week's content will also be divided into two parts. So first of all, I'll have recap of whatever is covered in this particular week. There is the technical content definitions and other things that are covered. I'll briefly discuss all of them and followed by the questions related to the content that is covered in this particular week. You may stop me at any point of this discussion and ask your queries if you have. I'll be happy to answer. Okay, so let's start with the recap of week 11 content. So this week started with the definition of this particular metric known as channel capacity. So in order to define what channel capacity is, we need another definition which is known as mutual information, which is defined something like this, like in this fashion. And what it says is basically it indicates how much information does a random variable y gives me about x, or how much information does a random variable x give me about the random variable y. And the channel capacity is obtained by maximizing this mutual information over all possible distributions of the input. Another important thing that was discussed was the Shannon capacity formula, which was C equal to W log 1 plus P average upon W n naught, where W is the bandwidth. This is the classical Shannon capacity formula, which is referred or which is considered as an upper limit of all the achievable rates for constellations. Another thing that was discussed was the capacity, or uh, or rather the spectral efficiency, that is R by W, was discussed, that is rate per bandwidth, which is given in bits per second per hertz. That was discussed for different constellation schemes. For example, we have it for MQAM and PAM, we have it for PSK, we have it for differential PSK, we have it for orthogonal signaling with coherent detection. So basically this is R by W, and this is SNR, that is EB by N naught, SNR per bit, EB by N naught in dB scale. And all the region above this is known as bandwidth limited, and all the region below this line, that is this line, is basically R by W equal to 1 line. So this is known as power limited region. So we had seen that when we are in this region, that is when we are considering these bandwidth limited constellations, then we had seen that as m increases, we had seen that the rate increases, bandwidth remains constant, almost constant, and that's why my R by W increases. Okay, another thing that we saw that, yeah, this R by W required increases with EB by N naught as well. Another thing that we saw in this power limited region was as m increases, here bandwidth increases, here rate also increases, but your R by W effectively decreases. And another thing that was discussed was your EB by N naught for PE increases with M, and for this your EB by N naught for PE reduces with M. These were some of the key observations that were done, and this was all about the comparison between different schemes, modulation techniques. After looking at channel capacity, the next concept that was introduced was communication through band limited channel. So initially we started with ideal channel, and then we went on for non-ideal channel. So what was discussed was for ideal channel we have this channel gain as 1, where mod f less than w. So basically your channel frequency domain response is like this. and your theta, that is phase of this thing, is a linear, or rather it has a linear phase, something like this. And if this is CF is a rectangular, then its equivalent in time domain will be a sinc function, which is given by this formula. So this is basically my channel impulse response. So this quantity here is channel impulse response. It was discussed that if we sample, or rather if we send the signals at integer multiple of 1 by w and set it as my symbol duration, then we get no ISI, and this is known as the Nyquist filter, and the maximum symbol rate that we can achieve is 2w in this case, which is nothing but 1 by t. Now this Nyquist filter is defined in general, which is basically convolution with a rectangular function in frequency domain, or multiplication with a sinc in time domain. Now when we are having this Nyquist filter, there are some issues with it. So first thing is it has an infinite tail. Your sinc decays with 1 by x thing, but it is like slow decaying thing, and yeah, it extends to infinity. And suppose we have a small deviation or small synchronization error, then that will cause to a large intersymbol interference. So what aim do we have? We need to design a pulse so that we get lower tail amplitudes. That is, we have faster decays, and the sampling durations, that is t, 2t, and so on. We should have nulls at the sampling durations. Like if I'm sending the signal at 0, then at t I should have a null, so that when I'm sending another signal at t, its peak will be there, and rather all the other symbols will be having a null, which won't create any intersymbol interference. Now in order to handle this particular issue of longer tail amplitudes, what was done was, instead of having a sharp uh, fall, like a sharp fall here, we can taper it down like this, and that can be done by considering a raised cosine pulse. The frequency response for this raised cosine pulse is given like this. Now here in this formula, this W is the absolute bandwidth. Like, what do we mean by that? So let's say the frequency response for this raised cosine goes something like this, and let's say this is minus W naught, and this is W naught, this is W, this is minus W. So your W is the absolute bandwidth, that is this entire bandwidth, and W naught, this quantity will be 1 by 2t, which is the minimum Nyquist width. And the role of factor, that is how much excess bandwidth we have with respect to Nyquist, is R equal to W minus W naught upon W naught, which is known as the role of factor. Now the time domain equivalent of this or the channel impulse response is given by this formula, and this W, this bandwidth, this much portion is given by 1 by 2 1 plus R into RS, where this RS is symbol rate. Now what exactly is happening? We are getting that the tails are 0 at the sampling duration. That thing is there. Why? Because we are getting a multiplication by sinc 2 W naught T. Another thing is these tails are falling with W naught in with inverse proportionality with this W square, which can be observed here. But an issue with this filter is it's still a non-causal filter. Now, in order to build this raised cosine thing, this is an equivalent thing that we are obtaining at the receiver end. So, in order to have a raised cosine, what we do, we have a root raised cosine at the transmitter and root raised cosine at the receiver, so that the equivalent thing that we are getting is the raised cosine pulse that we want. Okay, yeah. After looking at that, we went on and looked at like, okay, again we said that this has some issues because the rate reduces. the symbol rate that we were having here, that reduces because of this particular quantity here. Okay, so now the issue is how to have a better rate but still have less ISI or some controlled ISI and have a good performance. So that can be done by considering a controlled ISI thing, and in that case we looked at two different conditions. One was duobinary signal and another was modified duobinary signal. And for duobinary we'll have x and t as 1 for n equal to 0 and 1, and for modified duobinary x and t will be equal to plus minus 1 for n equal to minus plus 1. So this we had seen, and the general class of band limited partial response signals were given by this particular formula, where we can control these things in order to get the desired thing that we want, or the desired form of impulse response that we want. No, sorry, not impulse response, the transmission signal that we want. After that, we looked at the detection of duobinary signals. I won't spend time on this detection of duobinary and modified duobinary signals right now. We'll take an example while we are solving questions, and that will actually help you understand better what exactly is happening. So I'll skip this part right now and put more emphasize more on this when we are looking at the question that corresponds to this. And after doing that, we went on to see what are non-ideal channels. So we know that for an ideal channel we have frequency response like this. Now suppose the frequency response goes something like this, then it will be a non-ideal channel. Now in order to remove this kind of thing, like this abnormality that we are having in this, what we do is we go for equalization. In that we can go for minimum least square estimation or detection, or another approach is going for filtering. And that filtering can be a linear filter, which is basically zero forcing or MMSC, or it is a non-linear filter, which is DFE or turbo, or it is a preset or adaptive filtering, or it is symbol spaced or fractional spaced. We'll look at some of these filtering techniques in upcoming week. This week the zero forcing equalization was introduced, such that the equalization filter has an impulse response as 1 upon channel's impulse response. So this will reduce your equivalent channel response from equivalent impulse response from your transmitter channel receiver and your transmitter equalization channel and your receiver as oh, what nonsense I'm speaking, transmitter. So basically you'll have your transmitter, then you'll have your channel, then you'll have equalization, and then your receiver. So all of these four things will basically be leading to your raised cosine thing, raised cosine impulse response. So that's why in order to get a flat channel response, we'll cancel out the channel response introduced due to the non-ideality by setting equalization as 1 by HCHF. So because of this, this H equivalent of F can be written as 1 upon magnitude HCH of F into e power minus angle of HCH of F. I hope this part is clear. If you have any queries, then please let me know. And if there are no queries, we'll move ahead and solve some of the questions. Okay. Let's start with the questions that I had planned to cover today. So let's start with the first question. So what does it say? The capacity of a band limited AWGN channel is given by the formula C equal to W log 1 plus P by sigma square W log 2 bits per second, and for a fixed P by sigma square equal to 1000, we need to find the channel capacity in kilobits per second when your W, that is this bandwidth, is very large, that is it tends to infinity, that is you're having entire your AWG channel. Okay, so let's try to see how that can be done. So what do we have here is your channel capacity C is W log 2 1 plus P by sigma square W. Okay, now what I'll do is I'll multiply and divide by P by sigma square, so that will be something like this. Okay, so now what I'll do, I'll take this P by sigma square as it is here, multiplied by log of 1 plus P by sigma square W upon P by sigma square W. Okay, now let us take the limit W tends to infinity. This is to the base 2. Okay, so now this I can write as P by sigma square 1 upon log 2, natural log of 2, into limit W tends to infinity log, or rather this will be natural log 1 plus P by sigma square W upon P by sigma square W. Now as W tends to infinity, your P by sigma square W tends to 0, and there is a property of this limits. We know that limit x tends to 0 log 1 plus x by x, this thing is equal to 1. So if that is the case, then this limit from here, this limit will be equal to 1, and therefore what do we have here is P by sigma square into log e to the base 2. Now log e to the base 2 is 1.44 approximately, so this will be 1.44 into 10 raised to 3 bits per second, which is equal to 1.44 kilobits per second. Any questions at this part? Okay, if there are no questions, then let's go ahead and solve the next part. Next question. So what we need to do is we need to find the mutual information of a binary symmetric channel with crossover probability as P. Okay. So what do we have is, let's say this is your binary symmetric channel with input and output as 0 and 1. So this crossover probability is P, which implies that this probability is 1 minus P. And let's say the input is X and output is Y. Now another definition for this mutual information is basically uncertainty or entropy in Y minus entropy in Y given X. Okay, so this we have. So for a moment, let's try to derive this in terms of this P and this H of Y. Okay, let's try to do that. So let's try to find what is this H of Y given X. So this H of Y given X is given as probability that X takes a value 0 into H of Y given X equal to 0 plus probability that X equal to 1 into H of Y given X equal to 1. Okay, so now let us find out what is h of y given x equal to 0. So this will be equal to probability that y equal to 0 given x equal to 0 into log of 1 upon probability that y equal to 0 given x equal to 0 plus probability that y equal to 1 plus x equal to 1 into log of 1 upon probability that y equal to 1 given x equal to 0. Sorry, not 1, 0. Yeah, okay. Now this probability y equal to 0 given x equal to 0. Y equal to 0 given x equal to 0 is this 1 minus p. So what do we have here is 1 minus p into log of p, no sorry, 1 upon 1 minus p plus this probability is probability that y equal to 1 given x equal to 0. So this is simply p into log of 1 by p. Okay, and let's define this as hp, and this log is with base 2. Okay, now similarly let us find h of y given x equal to 1. So that will be again h of sorry, probability that y equal to 0 given x equal to 1 into log of 1 upon probability that y equal to 0 given x equal to 1 plus probability that y equal to 1 given x equal to 1 into log of 1 upon probability that y equal to 1 given x equal to 1. Okay, so this is what we are having here. Now again this probability of y equal to 1, sorry, y equal to 0 given x equal to 1 is this. So this will be p. So this will be p times log of 1 by p plus this quantity, probability that y equal to 1 given x equal to 1 is 1 minus p. So this will be 1 minus p log of 1 upon 1 minus p. Okay, this is what you are having right now. So this is also equal to hp. So therefore h of y given x is equal to probability that x equal to 0, let's say it is alpha, or rather let's say, okay, probability that x equal to 0 into hp plus probability that x equal to 1 into hp, and so we can take out this hp common. So what do we have is probability that x equal to 0 plus probability that x equal to 1. Now we know that this x has only two possibilities, which means that this quantity will be equal to 1. Okay, therefore h of y given x is equal to hp, and therefore if we see this equation of this mutual information, then we have this mutual information as h of y minus h of y given x. So we have it as so this is the mutual information that we are having. Any questions? Okay. Okay, if there are no questions, then let's move ahead with the third question for today. So what does this question say? We need to find the channel capacity for a binary symmetric channel with crossover probability P. So what do we know about channel capacity? So by definition, this channel capacity is given as max saw over the distributions h of y I of x comma y. Okay, this we had seen. So now what we have here is this C is max of, what do we have? Mutual information. We had found that in the last question. We had found this mutual information formula for equation in the last question, which is h of y minus, so h of y minus hp, and yeah, this mutual information is, so I can just write y here also. So let's see this with p of y. Now what we'll do is, let's see your y, this PDF of y, or PMF, sorry, the PMF of y is alpha if alpha equal to 1, no sorry, if y equal to 1 and it is equal to 1 minus alpha if y equal to 0. So therefore this h of y will be equal to alpha log 1 by alpha plus 1 minus alpha log 1 upon 1 minus alpha. Another thing to note here is this h of y is uncertainty, and in very initial lectures we had seen that this is less than or equal to log m to the base 2, where m is the number of values the random variable y takes. So here how many values does this random variable y take? Only two values, that is 0 and 1. So these are the only two values. So for our case, this m is equal to 2, and therefore this comes out to be log 2 to the base 2, which is equal to 1. So this we know that this h of y is less than or equal to 1. Now if we plug this thing in this equation, so therefore what do we have is, so the maximum value that this h of y can take, is 1. So this quantity will be maximized when this y, or this rather this h of y, takes a value as 1. And when do we achieve this? This inequality is achieved with strict equality when both these values are equiprobable, that is this alpha equal to half and this h of y is equal to 1 if and only if alpha is equal to half. Okay, so this we know. So now using this information, what do we have is this channel capacity, or rather instead of saying channel capacity, this mutual information will be maximized when we are having h of y as 1. So therefore my channel capacity is equal to 1 minus h of p. So this is the thing that we are having here. And what is this h of p look like? So this is p times log of 1 by p plus 1 minus p times log of 1 upon 1 minus p. So this comes out as 1 plus p times log p plus 1 minus p times log of 1 minus p. And this is basically a convex function which looks something like this. So this is p equal to 0.5, this is p equal to 1, and this is p equal to 0, and this gets maximized at p equal to 0 and 1. Any questions? Please stop me at any point. Okay, if there are no questions, then let's go ahead and look at the next question that I had planned to cover today. So yeah, so that what does this question tell? So it says that the transition diagram for a discrete memoryless source with 3 inputs and 3 outputs is as shown in the figure below, like in this figure. Now suppose this alpha is between 0.5 and 1. You need to find the alpha that maximizes this channel capacity. Okay, so now what we'll do is, let's say your x takes 3 values a, b and c with probabilities pa, pb and pc, and let's say this y also takes probabilities a, b and take values a, b and c, and this is the transition diagram that is given to us. Like this a gets is received as a with probability, or rather probability of receiving a given a was transmitted is 1 minus alpha. Probability of receiving b given a was transmitted is alpha. Similarly, this b can get converted, can be received as b or can be received as c, and the c can be received as c, and the c can be received as a. So this is the transition diagram that we are having, and we need to find the channel capacity. So in order to find the channel capacity, we need to find the mutual information. Okay. So what do we have is, let's say here ix comma y will be again equal to h of y minus h of y given x, and we know that this will be less than or equal to log m to the base 2, where m is equal to 3. Here we are having 3 possibilities. So this will be 3 to the base 2 minus h of y given x, and note that this is a positive quantity. Log 3 to the base 2 is a positive quantity. So therefore this is the maximum possible value for as this quantity will be depending entirely on alpha. So we'll see how that happens. So the claim is channel capacity is equal to log 3 to the base 2 minus h of y given x. Okay, so let's say this is my claim, and let me number it as equation 1. So now what we need to find is this conditional uncertainty, or this conditional entropy, which is h of y given x, which is obtained as, or which is by definition, we have it as probability of that x is equal to a into entropy that of y given x equal to a plus uncertainty that y, so probability that b was transmitted into h of y given x equal to p plus probability that c was transmitted into h of y given x equal to c. Okay, so this we have here. So now let us try to find out all of these quantities one by one. I'll just repeat this same page. So let us find out h of y given x equal to a. Now if x is equal to a, the only two possible values of y are this a and b. So this I can write as probability that y equal to A given x equal to A into log of 1 upon probability that x, uh, y equal to A given x equal to A plus probability that y equal to B given x equal to A into log of 1 upon probability that y equal to B given x equal to A. Now this quantity here, probability that y equal to A given x equal to A, is 1 minus alpha. So this thing we have as 1 minus alpha into log of 1 upon 1 minus alpha plus this quantity here, probability that y equal to B given x equal to A, is this, that is alpha. So we have it as alpha into log of 1 by alpha. So this again I can write as small h of alpha. So I had numbered 1, so this is equation 2. Now let us try to find out this quantity. Change the color of my pen. Yeah. So let us try to find out h of y given x equal to b. Now if x is equal to b, that is x is equal to b, then I can either I can receive b or I can receive c. So y can take only two values, either b or c. Okay. So in that situation, I can write this as probability that y equal to b given x equal to b into log of 1 upon probability that y equal to b given x equal to b plus probability that y equal to b, sorry, y equal to c given x equal to b into log of 1 upon probability that y equal to b, sorry, y equal to c given x equal to b. Okay. Now this probability of y equal to b given x equal to b is again 1 minus alpha. So this comes out to be 1 minus alpha into log of 1 upon 1 minus alpha. Similarly, this quantity, probability of y equal to c given x equal to b, is alpha. So this comes out to be plus alpha log 1 by alpha. Again, this I can write as small h of alpha. Let's say this is equation 3. So here the third value that we need to find is probability y given, uncertainty of y given y given x equal to c. So we need to find h of y given x equal to c. So this comes out to be probability that y equal to c given x equal to c into log of 1 upon probability that y equal to c given x equal to c plus probability that y equal to c given x equal to b into log of 1 by probability that y equal to c, y equal to a given x equal to c. Did I write here? Y equal to a given x equal to c. And why are we having like this? Because the c can either be received as a or the c can be received as c. That's why this y can take only two values, that is c and a. C and a. Okay. So this probability that y equal to c given x equal to c is again 1 minus alpha. So we have this as 1 minus alpha log of 1 upon 1 minus alpha plus this quantity y equal to a given x equal to c. Its probability is alpha log 1 by alpha, and again this is h of alpha. So if we substitute these equations 2, 3 and 4 in this equation of h of x given y, in this equation h of x given y, then what do we have is, so we have h of x given y is equal to alpha, pa h alpha plus pb into h of alpha plus pc into h of alpha Now one more thing you should note, and that is this PA plus PB plus PC is equal to 1 because they are probabilities, and A, B and C are the only three values that this particular event can take, and yeah, particular random variable can take. And yeah, this, if I take this h of alpha common, then I'll be left with PA plus PB plus PC, which will be h of alpha into 1, which comes out to be equal to h of alpha. So this thing is simply h of alpha. So now if we substitute this in our channel capacity or other mutual information equation, so what do we have is, here I of x y is less than or equal to log 3 to the base 2 minus h of alpha. Now an important thing to note here is this h of alpha. This quantity here is not depending on PA, PB and PC. It does not depend on the prior probabilities or any distribution of say x or y, which means that this quantity is independent of your distributions and only depends on alpha, which is the transition probability, which means that this itself is my channel capacity. Therefore my C is equal to log 3 to the base 2 minus h of alpha. So again I can write this as log 3 to the base 2 minus h of alpha, which will be plus alpha log alpha plus 1 minus alpha log 1 minus alpha. Now if we sketch this, okay, if we sketch only this alpha log alpha and 1 minus alpha log 1 minus alpha, then this thing will be something like this. This will be minus 1, this will be 0, this will be 1, and this is 0. Now if we add this quantity, so it will shift it upwards by this factor which is greater than. So it will be something like this. Okay, so it will be something like this, which means that this thing is alpha equal to 0.5 and this thing is alpha equal to 1, and we know that this alpha lies between 0.25. We have been given that this alpha lies between 0.25 and 1, so this somewhere here we are having 0.25. So this region is the one which we know, or which we are allowed to take the, or in which the alpha is allowed to take a value, and the value of alpha that maximizes it is this. So in allowed region of alpha, that is alpha belonging to 0.25 to 1, C is maximized when alpha equal to 1. Okay, as far as I remember, this was a question in GATE 2022 examination. You may check the past year papers for reference. Like, yeah. Any doubts, any queries in this particular question? Okay, if there are no questions, then I'll go ahead for the next question that I had planned to cover today. So 2-3 questions after this particular question will be based on your raised cosine pulses. So probably, yeah, 3 questions after this, like from this 3 questions will be based on raised cosine, and all of these 3 questions are taken from some year's gate. Okay, yeah, fine. So what is given is an ideal bandpass channel of 500 to 2000 hertz is deployed for communication. So what does it say is, we're having this 500 hertz and 2000 hertz, similarly like this, minus 500 hertz and minus 2000 hertz. This is what it says. Okay, it's deployed for communication. So it says that a modem is designed to transmit bits at a rate of 4800 bits per second. So the bit rate is given to us, which is 4800 bits per second, and the constellation that is used is 16 QAM. And what we need to do is we need to find the roll of factor with raised cosine that uses the entire frequency. Okay, now the equation that relates this roll of factor, bandwidth, and symbol rate, or let's say bit rate for that matter, is this W is equal to Rs by 2 into log of, sorry, y log into 1 plus R, where this R is your roll of factor. Okay, now what is this W? What does this W mean? So this W was basically something like this. This was W and this was minus W. Okay, so now this thing here, this thing is in baseband. And bandwidth in baseband is equal to W. Okay, however, if we have a situation which is something like this, or what I'll do is I'll take the same frequency response to band pass, which will be something like this. And if you observe carefully, this region, this entire width is 2W. So we have this width as again 2W. Okay, means let's say this is some FC, so this will be FC plus W and this will be FC minus W. So this thing is happening in band pass. And bandwidth in bandwidth here is equal to 2W. And in this particular question, what is given is band pass channel, which means that we have been given this value, that is 2W. So what will be 2W? It will be upper frequency minus this lower frequency, allowable frequency. So from this equation, from this thing, we have this bandwidth as 2000 minus 500, which is simply 1500 hertz. And note that this particular value is equal to 2W and not W. So when we are given a a band pass channel, then we have to take the bandwidth as 2W, and when we have been given a baseband channel, we have to take the bandwidth as W. This thing has to be kept in mind because it is important. And if in general it is not mentioned and it is said that we are deploying it for a communication channel, then in general you should assume that it is a band pass or it is a band pass channel, because we generally do a carrier based communication, so it will be always a band pass channel. So that thing you should keep in mind. Okay, so we are having this kind of situation, and the equation that we know is this. Okay, so let me add a page. So we have this W as Rs by 2 into 1 plus R. But now the value we have is for 2W, so we can just modify this equation by multiplying by 2 on both the sides. So we have it as Rs into 1 plus R. Now another information that we have been given is this, that we transmit the bits at a rate of 4800 bits per second, and the constellation that we are using is 16 QAM. Okay, so bit rate is given as 4800 bits per second, and the constellation that we are using is m QAM, which is for m equal to 16, which means that your k, that is number of bits, is log m to the base 2, which is log 16 to the base 2, which comes out to be equal to 4. And therefore your symbol rate is equal to your bit rate, that is 4800 upon 4, which comes out to be equal to 1200 symbols per second. So this quantity here is your Rs. So now we have this 2W, we have this Rs, and what we need to find is R, which is the only unknown. So let us substitute the value of this Rs and 2W in this equation. So this 2W we had obtained as 1500 Hertz. So let us substitute that. So this, from this equation, we have 2W is equal to 1500, which is equal to your symbol rate, which is 1200 into 1 plus R, and therefore 1 plus R is equal to 1500 upon 1200, which is equal to 5 by 4, and therefore my R will be equal to 5 by 4 minus 1, which is 1 by 4, which comes out to be 0.25. Any questions? Any doubts in this question? Okay, if there are no doubts, then let us go ahead and look at the next question that we need to solve. So what is given to us is consider a binary transmission. So what we are having is, we are having a binary transmission at a rate of 56 kbps using baseband binary PAM, and that is designed to have a raised cosine spectrum. The transmission bandwidth in kilohertz for roll-off factor of 0.25 is, so we need to find the transmission bandwidth. So what all things are given to us? Let us first note that down. First of all, we have binary transmission using binary pulse amplitude modulation. That is, we have m equal to 2, which means that k equal to 1, which means that my bit rate is equal to symbol rate, which is equal to rs, and we have been given this rs as 56 kilobits per second. So your rs is 56 kilobits per second. So this much information we have. Along with that, what is given is that we are using baseband communication. This is an important thing. We are using baseband transmission. Okay, so if we are having a baseband transmission, then what do we need to take the bandwidth as? So for a baseband transmission, your bandwidth will be equal to W, as we have discussed here. For a baseband transmission, we look at this much part as a bandwidth, so your bandwidth will be equal to W. So therefore, this implies that your transmission bandwidth will be equal to W, and we know that this W is equal to Rs by 2 into 1 plus R, and we have been given this R. We know that this R is given as 0.25. Okay, I hope this part is clear. So now let us plug in all the values that we know. So what all things do we know? We know this Rs, we know this Rs, we know this R. So let us substitute these values here. So we have W as Rs, which is 56 kilobits per second. So 56 into 10 raised to 3 upon 2 into 1 plus R is 0.25. And so this is equal to 56 into 1.25 upon 2 into 10 raised to 3, which is equal to, so if you solve this, this comes out to be equal to 35 into 10 raised to 3 hertz, which is equal to 35 kilohertz. And since it is a baseband communication, what do we have? Therefore, the transmission bandwidth is equal to 35 kilohertz. Okay, any questions? Okay, if you don't have any questions, then let's go for the seventh question that I had planned to cover today. So it says that an M-level PSK modulation scheme is used to transmit independent binary digits over a bandpass channel with bandwidth 100 kilohertz. So the information that we are having here is M-array PSK modulation scheme is used to transmit binary digits over bandpass channel with bandwidth 100 kilohertz. Okay, so M array PSK which means number of bits is equal to log m to the base 2. This we know. Then we know that it is a band pass channel. And what does this information tell us? This tells us that if it is a band pass channel, then your bandwidth will be equal to twice the value of your W. Okay. So this means that your bandwidth is equal to 2W, which is equal to 100 kilohertz. Okay. Then in next sentence, what is given is if the bit rate is 200 kbps and the system characteristic is a raised cosine spectrum with 100% excess bandwidth, then the minimum value of m is. Okay, so this is what is given. So bit rate is 200 kbps and we have the raised cosine spectrum with 100% excess bandwidth. So this 100% excess bandwidth means your R is equal to 1. So how to conclude that? So if we look at this raised cosine spectrum, so this is your W naught and this is your W, this is your minus W naught and this is your W, and we have it something like this. Okay, let me draw it nicely. Yeah, we have it something like this. And okay, so when we are having 100% excess bandwidth, then this W will be equal to 2W naught. This will be equal to minus 2W naught. Okay, so in that situation, so this part here that I am highlighting, if this width is equal to W naught, then it indicates that we have 100% excess bandwidth. Okay, so what it means that, what is this part? This part is basically equal to W minus W naught. So the definition for your roll off factor R is given as W minus W naught upon W naught. And we saw that for an excess bandwidth, 100% excess bandwidth, this W minus W naught quantity is equal to W naught. So what we have here is W naught upon W naught, which comes out to be equal to 1. Okay, so this much information we have. So we have bit rate, we have bandpass channel bandwidth, which is equal to 2W. We have the number of bits in terms of M, and we have the value of roll off factor. So what do we need to find? We need to find the minimum value of M such that all of these things are fine or all of these things are satisfied. Okay, so now what we have is, we know our formula that this W is related to your symbol rate and roll off factor as Rs by 2 into 1 plus R, and this Rs I can write as bit rate upon log m to the base 2 multiplied by 2 into 1 plus R. Now I can take this 2 to left hand side. So what do we have is, we have 2W is equal to bit rate upon log m to the base 2 into 1 plus R. Now this 2W is given as 100 kilohertz. So let's substitute this value. So we have it as 100 kilohertz, that is 100 into 10 raised to 3. Now this bit rate is given as 200 kbps. So this is 200 kbps. So this I can write as 200 into 10 raised to 3 upon log m to the base 2 into 1 plus r, and we saw that this r, or the roll off factor, is equal to 1. So this is equal to 1 plus 1. Okay, so now I can cancel out this 10 raised to 3. I can cancel out these zeros also, and I can take this log m to the base 2 to the left hand side. So what do we have is, therefore log m to the base 2 is 2 into 2, which is equal to 4, and therefore m is equal to 2 raised to 4, which comes out to be 16. So the value of m, so basically you can use 16 PSK constellation to achieve the given specifications. I hope that's clear. If you have any queries, then please let me know. Okay, so if there are no questions, then let's go ahead and solve the next question that I have planned to cover today. So what does it say? A binary sequence, this particular given binary sequence, is input to a precoder whose output is used to modulate the duobinary transmitting filter. Now, what all things do we need to show? We need to show the precoded signal, the transmitted amplitude levels, the received signals, and the decoded sequence. These are the 4 things that we need to show. So let us first mention what all things we need to show properly. So just to mention that the sequence Dn is 1 0 0 1 0 1 1 0 0 1 0. So this is my data sequence, and this data sequence is input to your precoder, and this precoder, so this precoder, what is the output of this precoder? The output of this precoder is Pn, which is basically Dn, that is the current data instant, minus your Pm minus 1, that is your previously precoded bit, or previously precoded data. Okay, and this thing is modulo m minus 1. Here m is equal to 2. I'm sorry, this is modulo m, so this is modulo 2, and this is my pre-coded sequence. Okay, so what it is doing is, it is doing a binary subtraction. So what does it mean? So if this thing is 0 and this is 0, then your Pm will be 0. If your Dn is 1 and your Pm is 0, then this thing will be 1, your Pn. I'm sorry, I made a mistake. This should be Pn minus 1. Yeah. Then if Dn is 0 and Pn minus 1 is 1, then again this will be 1. And if Dn is 1 and Pn minus 1 is 1, then this will be equal to 0. Okay, I hope this part is clear. So this thing is your pre-coded signal, Then we need to show your transmitted amplitude levels. And transmitted amplitude levels are IN, and these IN are given by 2pn minus 1 okay, so this is what you will transmit, that is 2pn minus 1. So if this pn is 0, then your in will be equal to minus 1, and if your pn is 1, then your in will be 1. Okay, I hope this much part is clear to you. So this is your transmitted amplitude levels. So this thing is transmitted amplitude levels. Okay, now your received signal will be having some noise. So now let us consider your received signal. Let's say it's noise free. Let us assume that we are having a noise free transmission for a moment. Rather, let's say just look at the noise free components. So let's say we'll look at this received signal. Instead of looking at ym, we'll look at bm, which is received signal or received sequence. And this received sequence is given as in plus in minus 1. So this is your received sequence. That is, you will go on adding the consecutive, like current and the previous pre-coded symbol, or sorry, not pre-coded, the transmitted amplitude levels, like that you will transmit. And now the next thing is your decoded sequence. So your decoded sequence, let's say it's d hat, and this, or d hat n, and this is equal to 1 if uh, if your y, or rather your mod ym, is less than 1, and it is 0 if your mod yn is greater than or equal to 1. So this is what we are having, yn. And from where is this thing coming? So if we go back and look at the content that we had written here, so your dm is basically half bm plus 1 mod m. Okay, so this is what we are having here, and from this equation we are landing up so from that equation we are landing to this particular thing. Okay, now here your yn is equal to bn, that you keep in mind, because your yn is basically bn plus nu n, which is some noise component. Okay, so this is what we are having here. Okay, so now let us try to look at the all of these 4 sequences, and let us try to construct a table for that. So what all things do we need to find? So we need your data sequence, so your data sequence is basically your dn, and that is 1 0 0 1 0 1 1 0 0 1 0. Okay, let me write it properly. Yeah, 1 0 0 1 0 1 1 0 0 1 0. So this is your data sequence. So let me just draw a line also between these so that these are distinguishable. So let me just separate them with this line for our better understanding. Okay. Okay. And yeah, another thing that we'll do is we'll write the value of n. So let's say n equal to 0 here, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 and 11. Okay, so this much thing we are having here. And yeah, just for sake what we want, I will just have a copy of this with me. Okay, so this is what we are having. So the first thing that we need to find is the pre-coded sequence. Okay, so what we need to do is we need to find pre-coded sequence, which is nothing but your Pn, and we know that this Pn is basically difference between the current data point and the previously pre-coded, the current data point and the previously pre-coded value, and the difference between them. And we had seen that this is simply like XOR between these two values. Okay, we are ignoring the carry, so it is simply your XOR thing. Okay, so basically what we need to do is we need to find an XOR between this current value and the previous value, XOR between the current value and the previous value, and like that. Okay, so now initially let us assume that at n equal to 0 the pre-coded value is 0. So this is an assumption that we are making. So now if I need to find the pre-coded value at n equal to 1, that is p1, then I have to find an XOR between these two values. So I'll need to find 1 XOR 0, and 1 XOR 0 is nothing but 1. Similarly, so for some initial thing, I'll draw this. So again, for okay, so for n equal to 2, I need to find XOR between these two. So that comes out to be equal to XOR of 0 and 1 is again 1. Then again XOR of 0 and 1 is 1. Now we have this 1. Then XOR of this 1 and 1 is 0. Then we have XOR of 0 and 0, which is again 0. Then we have XOR of 0 and 1, which comes out to be equal to 1. Then we have XOR of 1 and 1, that comes out to be equal to 0. Then we have 0 and 0, so again it will be 0. Then we have 0 and 0, so again that will be 0. Then we have 1 and 0, so this will be now equal to 1. And then we have this 0 and 1, so this thing comes out to be equal to 1. So this is the pre-coded sequence, which is 1 1 1 0 0 1 0 0 0 1 1. So after pre-coding, we need to get the transmission sequence or the transmitted sequence. So the next thing that we need to find, just bring these in center, 2 up away. So after that we need to find transmitted sequence, which is nothing but in, and this in is basically 2pn minus 1, which means that if we have pn as 0, then we'll set it as minus 1. Then if we have pn equal to 1, then we'll set it as 1. So what do we have here? We have it here as minus 1, 1, 1, 1, minus 1, minus 1, 1, minus 1, minus 1, minus 1, 1 and 1. So this is what we are having as your transmitted sequence. And after looking at the transmitted sequence, we need to look at your received sequence. So we need to look at received sequence, and your received sequence is nothing but your bn. Okay, and your bn is basically in plus in minus 1. That is, you need to take the additions of consecutive things. That is, first of all, you will find the addition of these two. So this comes out to be equal to 0. Then you will find the addition of these two. This comes out to be 2. Similarly, we'll find the addition of these two. That comes out to be again 2. Then we'll find these two, which is 0. Then we will find the addition of these two, that is minus 1, which comes out to be equal to minus 2. Then we'll find the value of these two, that is addition of these two, which again comes out to be equal to 0. Then we'll find the value of 1 and minus 1, which comes out to be equal to 0. Then we'll find the addition of these two, that is minus 1 and minus 1, so that comes out to be equal to minus 2. Then again we have minus 1 and minus 1, so that comes out to be again minus 2. And then we are having minus 1 and 1, so that comes out to be 2. Minus 1 and 1, that comes out to be 0. And 1, 1, and this comes out to be equal to 2. So your 0, 2, 2, 0, minus 2, 0, 0, minus 2, minus 2, 0, 2 is your received sequence. And now after that, what we need to do is we need to do your decoded sequence. So let me use some another color. Yeah, decoded sequence, which is, let's say, dn hat, and your dn hat is equal to 1 if your ym is less than 1, or in other words, if your bn is 0, then your dm is equal to 1, and if your bm is 2 or minus 2, then your dm will be equal to 0. So if it is 0, then we'll set it as 1. If this bn is equal to 0, then we'll set it as 1, and if it is 2 or minus 2, then we'll set it as 0. Okay, so what we are having here is, since it is 0, so this will be 1. Then we have 2, 2, so it will be 0, 0. Again 0, then it will be 1. Then we have minus 2, which means again 0. Then we have 0, zeros, then zeros are basically decoded as 1. Then we have minus 2, which is again 0, 0. Then we have 1, and then we have 0. So if you have observed carefully, since it was a noise-free transmit, or we have considered these noise-free sequences, or this received sequence, we have ignored the noise. So basically the thing that you have transmitted, the sequence that you have transmitted, we have recovered the exact same thing. However, when we are having a noise here, then it will have some errors. However, for this particular situation, for this noise free, just to understand what exactly is intended, by doing these kind of operations or this kind of pre-coding and then decoding technique for this particular thing, we are looking at how these things propagate and how each of the sequences constructed. Okay, so any questions at this point? Okay, if there are no questions, then let me go ahead with the next question. So what we need to do here is we need to repeat question 8 for modified duobinary signal pulse. So same thing we need to repeat for a modified duobinary signal pulse. So for that I'll just paste what I had copied. I'll just keep this as it is. Yeah. Okay. And I'll also draw what all things we need to find. So the first thing that we need to find here, I'll add -1 also. Yeah. So the first thing that we need to find is your data sequence, or rather we need data sequence we have written. We need to find your pre-coded sequence. So I'll just take this and do a copy paste instead of wasting time. Yeah. Okay. So this is what we are having. Let me remove one line. Okay. Yeah. So these are the 4 things that we need to find. So let's first just note down what exactly is being happening for this duobinary signal pulse. So we know that for this duobinary signal pulse, we have 1 at n equal to -1 and -1 at n equal to 1. So this kind of thing we are having. So this pre-coded sequence is PM, or rather let's say Pn, and this is obtained as your Dn plus your Pn minus 2, and this will be modulo m, and here it is a binary thing, so this will be modulo 2. So this is simply modulo 2 addition. So this is your pre-coded sequence that we are having. Then your transmitted sequence, the transmitted sequence so your transmitted sequence In is basically is again 2Pn minus 1, which again implies that this will be equal to 0 if, like, okay, let me write it here. So if this quantity is 0, Pn is 0, then your In will be -1, and if your Pn is 1, then your In will be 1. So this we had seen, this is the same as we had done in our previous thing also, like for duobinary. So same thing is used in modified duobinary also. Okay. After that we have the received sequence Bn. So this is your In, this is your Bn, and received sequence again we'll consider noise free. So here this Bn, we know that we at n equal to 1, n equal to 1 we have, at n equal to 1 we have 1. So therefore the current thing will be in, and at n equal to minus 1 we have minus 1, and the ulta. So we have it something like this, in minus 2. Okay. So this is what we are having, and then we have your decoded sequence. So your decoded sequence, let's say dn hat will be equal to half bm mod 2. So now let us see the possibilities for this. So if my bm is 0, okay, so now this in can take value 1 or minus 1. So this bn can take value 1, 2 and minus 2. I hope that thing is clear. So okay, again I made a mistake here. It should be n. Yeah. So if this bn is 0, then your dn hat will be again equal to 0. If your bn is 1, then your if your bn is 2, then your dn will be 1, and if your bn is minus 2, then your dn hat will be minus 1 mod 2, which is again equal to 1. So if I have received 0, then I'll decode it as 0, and if I receive it as 2 or minus 2, then I'll decode it as 1. Okay, I hope that is clear. Now let us try to use these four equations and build our table which we had written here. So let's start to do that. Yeah. So this is our data sequence that we are having, that is 1 0 0 1 0 1 1 0 0 1 0. This is what we are having right now. And for precoded sequence, what we need to do, we need to consider data point, the current data point, and precoded point at two places before that. For example, if I'm decoding at if I'm precoding for n equal to 1, then I'll look at precoder value at n equal to minus 1. Similarly, if I'm looking at n equal to 3, then I'll look the precoder value at n equal to 1. So it will go like this, like this. Okay, and what we need to do? We need to do modulo 2 addition. So again, quickly if we do it, then if this is 0 0, then this will be 0. This is 0 1, then this will be 1. If this is 1 0, then this will be 1, and if it is 1 1, then it will be 0. Okay, so again this is nothing but simple XOR operation. Okay, I hope that part is clear. Yeah. Okay. So let us look at your precoded sequence that we are having. So let's say at n equal to minus 1 and n equal to 0, your precoded sequences were 0 and 0 without loss of generality. So now at n equal to 1, what I'll do an XOR operation for these two. And that will give me XOR of 1 and 0 as 1. Now for n equal to 2, I'll look at these two values. So this will give me a 0. Then I'll look at these two values. So XOR of 0 and 1 will be 1. Then I'll look at these two values. Again I have XOR of 1 and 0. So that comes out to be again 1. Then I'll look at these two values. So 0 and 1, again I'll get a 1. Then I have 1 and 1. So XOR of So XOR of 1 and 1 comes out to be 0. XOR of 1 1 again, so this comes out to be 0. Then we have XOR of 0 and 0, that is also 0. Then we have XOR of 0 and 0, that is also 0. Then we have XOR of 1 and 0, that comes out to be 1. Then we have XOR of 0 and 0, that comes out to be 0. Okay, so the pre-coded sequence that we have is, if we start from -1, it will be 0 0, will be 0 0, 1 0, 1 1 1, 0 0 0 0 1 0. So this is your pre-coded sequence. Now what do we need to get? We need to get your transmitted sequence IN. So if we have Pn as 0, then your IN should be equal to -1, and if your Pn is equal to 1, then your IN should be equal to 1. Okay, so let us try to do that also. So if your Pn is equal to 0, then your IN will be equal to -1. If your, again we have 0 -1, now your Pn is equal to 1, so for 1 we have your IN as 1. Then for Pn equal to 0, again it will be -1. We have 1 here, so 1, again 1, again 1. Then we have Pn as 0, so it will be -1. Again it will be -1, -1, -1. Now we have Pn as 1, so at n equal to 10 we have Pn as 1. So now this will be equal to 1, and here at n equal to 11 we have 0, so this will be -1. So this is your transmitted sequence. Okay, so now we need to get your received sequence, and your received sequence is given by this decoded sequence. Your received sequence is given as IN minus 2. So basically you need to subtract IN minus 1 from your IN. So it will be something like this: 1 minus of -1. Similarly, -1 minus of -1, like this. Okay, so let us try to do that. So at n equal to 1, we have 1 minus of -1, so that comes out to be equal to 2. Then at n equal to 2, we have -1 minus of -1, so this comes out to be equal to 0. Then at n equal to 3, we have 1 minus 1, that comes out to be equal to 0. Then at n equal to 4, we have 1 minus of -1, which is again equal to 2. Then we have 1 minus of -1, so this is equal to 0. One minus 1. Then we have -1 minus 1, so this comes out to be -2. Again we have -1 minus 1, so this comes out to be -2. Then we have -1 minus 1, this comes out to be 0. Then we have -1 minus 1, this comes out to be equal to 0. Then we have 1 minus of -1, we have 1 minus of -1, and this comes out to be equal to 2. And then we have this -1 minus of -1, so this comes out to be equal to 0. So the received sequence that we are having is 2 0 0 2, 0 minus 2 minus 2, 0 0 2 0. Okay, and the next thing that we need to find is this decoded sequence, and we had seen that for this decoded sequence, if we receive 0, then we'll decode it as 0, and if we receive it as ±2, then we'll decode it as 1. Okay, so what we have here is, so the first thing that we are receiving is 2, so we'll decode it as 1. Then we have 0, so we'll decode it as 0. Again we are getting a 0, so we'll decode it as 0. Then we are receiving 2, so we'll decode it as 1. Then we are receiving 0, so we'll decode it as 0. Then we are receiving -2, so -2 has to be decoded as 1. Then again we are receiving a -2, so we'll decode it as 1. Then we are receiving a 0, so we'll decode it as 0. Then we are receiving again a 0, so we'll decode it as 0. Then we are receiving a 2, so we'll decode it as 1. And then we are receiving a 0, so we'll decode it as 0. So this is your decoded sequence. And again, if you compare your data sequence that you had transmitted and the data sequence that you had decoded, since we had considered a noise-free case, noise-free transmission, these two are same. Any questions? Okay, if there are no questions, then let us move ahead with the last question that I had planned to cover today. So this question is based on your zero forcing equalizer. So what it says is, if a channel has an impulse response as ht equal to e power minus at ut for a greater than 0, we need to find hch of f. So this hch of f is the channel, the transfer function or the frequency response for your channel, and this heq is your is your transfer function for your zero forcing equalizer. Okay, so this is what we need to find. Okay, and we had seen initially that this h equalizer is equal to your hch. So how it is happening is, we are having your tx, then we are having your channel, then you're having your equalizer, and then you're having your receiver. And we know that this transmitter and receiver, these two are basically resulting in raised cosine. Okay, and so it means that if I want here, I want raised cosine, okay, so which means that these two should cancel out the effect of each other, or rather this equalizer should cancel out the effect of this channel in the given bandwidth. So for that, for zero forcing, equalizer, we have Heq of f is equal to 1 upon Hch of f. Okay, so this is this we know, this we had discussed earlier also. So now let us first find out what is your Hch of f. So Hch of f is simply Fourier transform of your channel impulse response, that is ht, and which is by definition equal to integral minus infinity to infinity ht into e power minus j 2 pi ft dt. So now this I can write as integral minus infinity to infinity e power minus at ut into e power minus j 2 pi ft dt. Now this thing here is not equal to 0 for all t greater than 0. So I can change the integral limits and drop, or rather I can write this as this is equal to 1 for all t greater than 0 and not equal to, and yeah, equal to 0 for all t less than 0. So then I can drop like I can change the limits from 0 to infinity and drop this ut function. So this comes out to be integral 0 to infinity e power minus at into e power minus j 2 pi ft dt. This I can write as integral 0 to infinity e power minus a plus j 2 pi ft, sorry, e plus j 2 pi f t dt. So this comes out to be e power minus a plus j, or let me just do that on next page. Therefore here hch of f comes out to be e power minus a plus j 2 pi f t upon minus a plus j 2 pi f evaluated from 0 to infinity, and this comes out to be, this comes out as 0 plus 1 upon a plus j 2 pi f. So this is equal to 1 upon a plus j 2 pi f. Now this thing I can also write as this hch of f, you can write as mod hch of f into e power minus angle of hch of f. So this comes out to be, sorry, by minus, not minus. I think I wrote minus initially also. No, this is fine. Okay, so the magnitude of this quantity will be 1 upon under root of a square plus 4 pi square f square and e power j tan inverse of 2 pi f by a. So this we'll have a minus sign here because it is in the denominator. And for zero forcing equalizer, we have this h equivalent of f as 1 upon hch of f, which is equal to a plus j 2 pi f, which I can write as its magnitude, which is under root a square plus 4 pi square f square into e power j, or yeah, let me write it, e power j tan inverse of 4 pi f by a, and this thing here is 1 upon magnitude of hch of f into e power minus j times angle of hch of f. Okay, I hope this is clear. This is the same thing that we had seen earlier. Yeah, same thing. This is the same equation we had seen for our zero forcing equalizer. So this is what we wanted to derive in this last question. If you have any questions, then please let me know. This was all I wanted to cover today. If you have any questions, then you may ask. Otherwise, you are free to leave the meeting. Thank you for attending today's session, and I hope to see you all in the next session as well.